Hello everyone. In this video I'm going to talk about kinematics and kinetics of particles in spherical coordinates. If you watched my playlist dynamics, you have seen that I have taught the kinematics and kinetics of particles in Cartesian, in cylindrical, and also in what we call path or tangential normal by normal coordinates. The only coordinates I have not covered so far is spherical, so in this video I'm trying to do that. So in spherical coordinates, the position of the particle here at point A is given by three values, and that's a radial distance r, which is directly from the origin to the point of interest, as opposed to the cylindrical one, where r was basically the projection of the position vector onto the xy plane. So in cylindrical, this is r, not that one. Here, r is the total distance, and then you have two angles, phi and theta, where typically theta, if you know from your courses, this angle is called the azimuth angle. Okay, and the other angle, which is your angle with respect to the z-axis, or in this case, the angle is defined with respect to the xy plane, this phi angle here. That angle is called elevation. Okay, so this angle in some textbook, it is this one as opposed to that one. Many textbook, they consider what? They consider this to be the angle phi. In our case, we are doing 90 degrees minus that. Okay, so we are measuring with respect to the xy plane. And this one, as I said, this angle is typically in the books, it is called the elevation angle. So three values, two angles, one distance. And so clearly you also have three position vectors. And these position vectors are called ER, E theta, and E phi, and they are in the direction of increase for R, theta, and phi. And these unit vectors, of course, none of them is constant in terms of direction. They all have they are unit vectors. They have constant magnitude of 1, but clearly as the particle moves from point to point, ER, E theta, and E phi, they will all change direction, so they all have time derivatives. And that has to be accounted for when we calculate velocity and acceleration here. Okay, so now, as I said, it's obvious that the position r is clearly along ER vector, right? And the magnitude of it is r, so the position vector r is clearly magnitude r in the ER direction. Now, the three unit vectors you have, you can show that ER, E theta, and E phi can be written in terms of ijk, the unit vectors of the Cartesian, as follow. ER is cosine theta cosine phi I, plus sine theta cosine phi j, plus sine phi k, and then E theta and E phi. And if you're wondering how these are even obtained, I can show you a couple of them. For instance, if you look, ER, okay, ER, if you look at it, you can break it down into basically a horizontal component and a vertical component. And this angle here is clearly the phi angle. So this vertical component is clearly E phi times sine, correct? So this one is sine of phi. And this horizontal one is, of course, what? This is cosine of phi. Right? And as I said, this angle is phi, phi, not alpha. Here. So you see that the z component is going to be a sine phi, as you can see here in the k direction, but the horizontal component is cosine phi, which is now going to be projected along this line. Okay, so that's cosine phi, And now that cosine phi has this angle theta with respect to what? The x-axis. So when you project that 1 times cosine phi, that cosine phi component, along the x, you have to also multiply it by cosine of theta. So it's going to be cosine phi cosine theta. And for y, the cosine phi component has to be multiplied by sine of theta. So you get cosine phi times sine theta in the j direction. So you see it's completely what? Obvious how you get what? You get the ER component. On the other hand, if you want to see how E theta is just those two components, well, it's quite clear that E theta here is like this vector. Okay, it's perpendicular to this radial direction. This is E theta. And let's see. Well, the problem is my pen is not working, so I use my mouse or finger, and that's of course not going to be beautiful. So clearly here, since the angle of E theta is theta plus pi over 2, so the x component is going to be cosine of theta plus pi over 2, which is negative sine theta, and the y component is what? Sine of theta plus pi over 2, which is what? Cosine of theta. And E theta has no vertical component. And finally, E phi, this guy here, this E phi, is clearly the cross product of what? Those two former vectors. So it is ER cross what? E theta. And if you carry cross product between these two vectors, I'm sure that if you use a 3 by 3 determinant and carry the cross product, this is going to be the result. For instance, let me just show you the z component of it, which is not really so hard to calculate. Okay, so if you want the z component of it, how would you do it? Well, for the z component, what you need is to cross the I component of that with the j of this, and then the j component of that with the I of this. And if you do it, I cross j is going to be k, so you're going to get a cosine squared times cosine phi, correct? So you're going to get cosine squared of theta times cosine phi. And then here you have j cross I, and j cross I is negative k, but this one has another negative, so it becomes positive, and it's going to be sine theta squared cosine phi. And clearly, if you factor out cosine phi between these two terms, you clearly can see that sine squared plus cosine squared becomes 1. So the result is equal to what? Is simply equal to cosine of phi, which is this guy. So you see, clearly you can get these three vectors. So this decomposition is absolutely what? Correct. These three vectors as we showed it. And then, as I said, now when you do want to calculate velocity, you have to take a time derivative from the position equation, correct? So how would you do that? Well, that should not be very hard to do, huh? Because all you need to do is to take time derivative of this equation here. And how would you do that? Well, if we want to take time derivative of that, the time derivative of this guy, let me bring it here. The time derivative v is going to be what? It is going to be r dot times er, because r can change, and then plus what? Plus, basically, let me see if I can move this now. And then plus r times derivative of er, like that. And the question is, what is the derivative of er? What is this guy? And you can easily show that the derivative of er can be written in terms of the other two vectors. it is theta dot cosine phi e theta plus phi dot e phi. Okay, so you replace that into the second one, so you will get r dot er plus what? R times theta dot cosine phi e theta plus r phi dot e phi, and guess what? That is exactly what you can see over here. That is your v. This term, the first term, is because your particle is getting radially closer to the origin or further away from the origin. This term here is the transverse velocity that you have because the azimuth angle is changing. And in cylindrical, we also had this r theta dot, but here, because of the angle phi, we have to project it along e theta, so we need to do a cosine phi. And our phi dot is because the elevation angle is changing, so you get our phi dot in the e phi direction. And now if you take a time derivative from the v, now you have a bunch of terms that are changing because now r dot can change, right? So here, r dot can change, er can change, r can change, right? Theta dot can change, cosine of phi, because phi is variable, can change, e theta can change. And here r and phi dot and e phi can change. So you see, here is a product, so you're going to get two terms. Here is four terms multiplied, so you're going to get four terms. Here is three, you're going to get three terms. And then when you simplify all these 9 terms, you're going to get this big bottom equation for what? For acceleration, where you can see that in the ER you have 3 terms, in the E theta you have 3 terms, and also in the E phi you have 3 terms, and that is exactly those 9 terms that I mentioned, 2 plus 3 plus 4. Okay, so clearly your acceleration is going to have 9 terms in it, and it's not as beautiful as the one that you had in cylindrical where you only had 5 terms. Here you have 9 terms in it. Okay, and some of these terms might be kind of understandable, like this one is because the r dot is changing, right? And this one looks like a centripetal acceleration, and then it has to be decomposed. This is another centripetal acceleration because phi dot is changing, because when you're doing a spherical coordinate, you have two kind of spinning motion. You can keep r fixed and rotate theta, then you move on a circle like this, a horizontal circle, or you can do what? You can keep theta fixed and turn phi, and then you're going to go on a vertical circle like this, okay? So you're going to go on something like this. So because of each one of them, you have r theta dot squared and r phi dot squared. So you're going to have 2 centripetal terms, as you can see. And then here, this r theta double dot, that's your transverse term. And here, these two are interesting. If you look at these two, they are what? In them, here is theta dot phi dot. So this is because both angles are changing. This one is because r and theta dot are changing. So this one is a Coriolis acceleration. These two are what? These two are like centripetal acceleration. Okay, or normal acceleration, you might call it. Let's see. So these are kind of like a normal acceleration. This guy is like a transverse acceleration, a transverse. And here, again, this is like a Coriolis one, as you can see. This is a component of the centripetal one. And this is another what? This is another transverse one. This is, of course, a radial direction, which also is in the n direction. And this term is an interesting guy here. That is the first time you see this term that you have not seen in any other one. So here you fix r, but you change theta and phi at the same time. So basically it means that you move on a diagonal circle, okay, because theta and phi are changing at the very same time, and that is very interesting, huh? So here you take a mix of these two circles. Not only you go circularly up and down, or you also move on a circle left and right. Okay, so you can say I go diagonally here. Okay, something like that is what you do. Oh, let's see. So you do something like this. Okay, and this is an interesting term that does appear. And if this is V and that is A, then you can, of course, once you have acceleration, you can use the Newton equation, sum F equal ma. And if you decompose F along what? Along r, theta, and phi, and also A has components along r, theta, and phi, then you're going to get these three equations, which are the equations of motion for the spherical coordinate. So clearly sum FR equal MAR, and AR is what? AR is this whole thing. That is your AR, which you can see over here. Sum F theta equal MA theta, and A theta is that whole thing, right? Let me see if I can use my hand. And as I said, sorry, this time I don't have my pen working, so you see this inconsistency in writing. And of course this one here is your A phi, this last one here. So these are the equations of motion, and this V, A, and the position are what? These are your kinematics equations. So now that we have kinematics and kinetics equations, it is time to what? It is time to look into one example. Now the example here is about satellite motion around the Earth, and we assume that the satellite moves in a circular orbit with a constant radius. Okay, so this r, this radius of the satellite, this guy is constant, and if it is, that means that your r dot and r double dot, they are both what? They are both 0. Also, for angle phi, for the elevation angle, we assume that is also 0. So the satellite is orbiting in the equatorial plane. So phi is 0, and so phi dot and phi double dot, they are also 0. Okay, and this phi of 0 is constant. So if that's the simplest scenario you can possibly imagine. Okay, that makes many of these terms of these accelerations, AR, A theta, A phi, to all go to 0. So here, the only force, of course, if you draw the free body diagram, the only force that is acting on the satellite is toward the Earth. So that is only an FR component, and that comes from the gravitational attraction, which is going to be GMM over R squared, where G is the universal gravity constant, gravitational constant. M is the mass of the satellite. Capital M is the mass of the Earth. R is the radial distance, and it's in the negative radial direction because radial direction is outward. So that's your FR. There is no force for theta and phi. So if you plug in a 0 here, a 0 here, and that's negative M G over R squared for FR, then you're going to get these three equations down below here. And you can see that the first equation, which is FR equal MAR. Now, since R is constant, this first term goes to 0. And since phi is constant, that term also goes to 0. Okay, so clearly the only term that is remaining for you out of the first equation is this r cosine phi squared times theta dot squared. This one is staying, and then the negatives would cancel. So that negative and this negative would cancel, and there should, and the m can also cancel. You can get rid of one m. So your equation becomes r cosine phi squared theta dot squared equals gm over r squared, and phi is 0, so cosine phi is 1. So your simple equation becomes r theta dot squared equals gm over r squared. You divide both sides by r and take a square root, and that gives you what? The angular velocity for rotation of the satellite around the Earth. So as this guy goes around the Earth with angular velocity, what? Theta dot, that's the formula, gm over what? R cubed, the square root of that. So g and m are fixed. So clearly, you see the angular velocity is proportional to what? To the square root of 1 over r cubed. So what does it mean? It means that, for instance, if you make the distance from the planet Earth 2 times higher, then this under the square root becomes 1 over 8, and the square root of 1 over 8 is 1 over 2 square root 2, okay? And that means what? Bigger r is, of course, corresponding to slower rotation, and smaller r corresponds to bigger rotation. And you see that this is proportional to what? Of course, 1 over r to the 3 over 2, or 1.5. Okay, so that is this formula. What happens to the other formulas? Well, remember, in other formulas, the derivatives of r and phi are 0. So this r is 0, and then this phi is 0, this phi double dot is 0, this phi dot is 0, this one is 0. So clearly, if you look in this equation, and of course there is no phi, so this equation clearly becomes 0 equals 0, which is of course satisfied. And what about that equation? If you look at this equation, cosine of phi is what? 0. Cosine of 0 is 1, and you can get rid of m here, right? Because the left-hand side is 0. So the thing that you will get is r theta double dot is 0. And r is not 0, so the only solution is theta double dot is 0, which means that theta dot has to be constant. And guess what? It is a constant. We just found it. This one here is what? A constant, as you can see. Because once r is constant, g and m are constant, then theta dot is constant. And that means what? Of course, that means theta dot is constant, or theta double dot is what? Is equal to 0, which you see this equation is also satisfied. So here we got all 3 equations satisfied if theta dot changes according to this formula that we just derived, this one. Theta dot, the square root of gm over r cubed. And this is a simple equation for the spinning of a satellite in equatorial plane about the Earth in a circular orbit of constant radius. Okay, so we use these equations. Hopefully this explanation was useful to you. You saw that how we described the position in this frame, how we described velocity and acceleration in this coordinate, and using which equation we can describe what? Kinetics of the particle. Also, you can easily show these derivatives of these unit vectors in terms of the other unit vectors, and it's not really hard to show that. All you need to do is to take a time derivative out of, let's say, ER, which involves terms like theta dot and phi dot multiplied, right? And here too, and then write it in terms of E theta and what? E phi here. So you can do some algebra and prove all of these 3 important what? Properties for the time derivative of these vectors. Okay, thank you so much for your attention. And I'm gonna see you in my next video. Thank you.